cluster, advanced clustering algorithm, the chapter 11. Then I think I can finish the lecture around 8 o'clock or 8:10. Then we will have the 20-minute discussion time regarding to the term project. Okay, so that's which is based on the vote that you performed the last week. Okay. So this is the quick summary of the last one that we covered, that we discussed before the snowstorm. We model-based clustering. What is the by the way, clustering algorithm? Anyway, there might be the limitation in machine learning. Even though we have the fancy, nice, perfect, if you attend nowadays we have a lot of the dissertation, presentation. Also, when you read the article, whether when you watch the news, sometimes the CNN have the news about something intelligent system or intelligent the robot or the machine learning or data mining, big data. But anyway, there might be limitation in computer stuff. Computer, even though we have the supercomputer like the Watson computer in IBM, so it's anyway computer. It doesn't look like the human being. Human being can infer, and the creative, sometimes the genius guy can imagine something, the very creative, the equation like the E equal mc square or whatever. But the computer cannot do that. It's mostly based on the pattern mining. Whether a computer can find a pattern which is the structured data. Okay. So association rule mining is also pattern based. If frequently happen, if you can find the frequent item, that's the pattern, that's the knowledge. You can find something, the rules, okay, as you have done in your exam. Also, what about the classification that we are going to discuss after spring break? Classification, you'd like to classify the data or data item based on certain criteria. How can you find such a criteria? You need to train. Training means it's kind of the frequent. You'd like to find the pattern, okay? That pattern can be parameterized or something the value or something the decision, okay? Then we can classify the data based on the training. What about the clustering? Clustering is also same thing. If data are similar, we'd like to put such a data into same cluster, same group, same class, otherwise the another. So that is based on, so clustering is slightly different from the other training based, the data mining approach. Okay, so clustering, so we have discussed about from the k-means algorithm or the bottom-up approach, hierarchical clustering algorithm, bottom-up approach or top-down approach, whether we can merge or whether we can split. Okay, so which are based on anyway the similarity or dissimilarity or distance sometimes. So that is the very important part. So when you cluster data, first you need to characterize your data set. Whether you can measure similarity or dissimilarity. Without such a similarity or dissimilarity, there is no way to cluster the data. Okay, so what about the model-based cluster? We are going to consider such a cluster as a model. What kind of model? Statistical model. Okay, so when we consider such a cluster as the statistical model, we can consider such a cluster with the probability density function f1 through the fk. So we have learned in the statistics such a probability, the probability of the data set based on the cluster. Okay, in this case the distribution. We will see why we consider such a distribution. To simplify the problem, we will use parameterized distribution, like the normal distribution, Gaussian distribution, some Poisson distribution, because they can be represented by the 1 or 2 parameter value. In other words, the problem is simplified. Identifying such a parameter value, that's it. Okay, so how can we define such the probability of your data based on the cluster. So it's a set of cluster. It's a set of data that can be, it's a likelihood function. So when you measure such a probability, it's the product of all the data item for that the probability density function. So for each the data item from 1 to, if you have the millions, so you need to multiply the millions of that by applying for each data item, for each cluster, what is the weight of the probability density function. Like the 10% for the cluster 1, 20% for the cluster 2, something like that. Then what is the weight of that? What is the membership? It's just kind of soft membership. If you already read the paper for the lab 2, okay, so regarding to the clustering algorithm, so there are two different membership, hard membership, soft membership. Soft membership can be considered as a fuzzy membership, okay? So the data item can belongs to only one or more, okay? But hard membership is either this one or nothing. So 1 or 0. But the soft membership, so it's a soft membership, and it has a weight, and you can, if you product all of this, the probability density function, you can have such a probability. Our goal is to maximize this value. Okay, that means it's a cluster correctly. That's the kind of goodness measure. That is the reason, even though we do not have the class label, the classification we have the ground truth data. Then we can train. So in this case, this is true. In this case, this is not true. In this case, this is true. Then we can find something parameter value or decision. Okay, but here we do not have such a thing. Instead, we try to optimize, maximize this value. That means that is the good clustering. Okay, at that time we can use, mostly we use such a parameterized distribution to simplify the problem, and also that is true. Why? So because of the central limit theorem, so it can be represented. If we reorder random variable, okay, it will be close to the Gaussian distribution. The idea is so if something happens frequently, that will be the mean value, right? So average. And this rarely happen is the mean. Okay, it's a Gaussian. Anything, if we reorder based on the frequency, it will be Gaussian. Anything, any event. So that is the idea of the central limit theorem. So because of that, if you read the technical paper, most of the model-based approach is a Gaussian something, Gaussian model, Gaussian mixture model, or the univariate Gaussian model, or multivariate Gaussian model, one-dimensional Gaussian model, two-dimensional Gaussian model, something like that. Okay? So this is a univariate Gaussian mixture model, 1D cases. So this is the probably best PDF Gaussian. The PDF of the Gaussian function, you probably see a lot of time for that function. I still struggling to memorize that. So I never tried to memorize, but anyway, this is the, you can see that there are two parameters. One is the variance and another one is the mean value, the mu and the sigma. So our goal is to find a set of the average mean value, a set of the variance. That's it, that is the clustering problem. Then there are different, so Gaussian mixture model means, so we have the multiple cluster, multiple distribution. How can you find it? So we can, actually the k-means is a special case of this system. Is expectation and maximization. It's a kind of the system. It's not the algorithm. It's kind of algorithm to find such a parameter value. So expect in the statistic, so EM algorithm consists of two steps. One is the E step and another one is the M step. E step means the expectation. So assign the value. Why don't you remind the k-means algorithm? When you find the K cluster using the k-means algorithm, first from the initial centroid, you try to find for each data item, you try to decide which centroid is the closest one, right? Once you decide, then you can form a new cluster, then find a new center weight. Okay, which means find which cluster belongs to, then compute the new center weight. Same idea. So in the E step, you assign the object to the cluster. Find which one. But at this time, this is not a hard membership. Instead, it's a fuzzy, soft membership. Percentile and weight and probability. Then during the M step, our goal is to find the new center weight, which means new parameter. As long as we know the parameter value, mean and variance, we can find the distribution. We can find the which Gaussian, the model, which means we can find the cluster. So that is the E step and M step. So this is an example of the E step and the M step EM algorithm. It's a simplified problem. In case we have the sixth value, let's see the initial value is A and B. So for the A and B, we'd like to find the distance from each the data item. From A, C, A, D, A, B, C, E, and A, F, and some sort and D, and so on. So this is an assignment. How can you find that there is a equation to find such an assignment? It's like the sum of the distance to the each centroid, then what is the distance for the cluster. So it's kind of weight for each centroid. From the C, what is the weight? What is the weight? So for example, the C, A, B, C point to the A centroid 1 is the 0.848, and the to the B is the 0.51, which means the 48% belongs to the A and 52% belongs to the B. In case the hard membership like the K-means, we are going to decide this is a 0, this is a 1, right? Because it's a hard membership, either or. But in case of the purging membership, like the EM clustering algorithm, we will use the soft membership, and so on. Then we can find the new centroid for the C1, the 8 point something, 5 point something, and iterate until converge, not changing. So that is the EM clustering algorithm. Actually, basically same as the K-means is a special case of the EM clustering algorithm. So if you read the paper for the second reading assignment, it's like exactly the same idea. Okay. So that is the EM. Nowadays, there are kind of trend. So when I was a student, almost all the dissertation and new paper, they use the EM clustering. It's kind of the new idea. So even I adapt EM clustering algorithm to cluster the moving object which are extracted from the video stream. So to cluster the moving object, I apply the EM clustering algorithm. My contribution is the first one to apply the EM clustering for the video data mining. That was the contribution at the time. Okay. So Gaussian mixture model, so we already discussed. So if we apply such a Gaussian mixture model for the EM clustering, it's the same idea. Okay. So during the E step, we can assign the each object for the cluster, which means each parameter. Then recalculate the parameter value. Okay, that is the mu and the sigma based on the Gaussian PDF. Okay, probability density function. Okay, then we can do that. Strength. Okay. Because it's based on the model base, it's a cluster. Even though we have some missing data, it works very well. Okay? Because so think about the find something Gaussian model. Even though we miss some of the data, so it formed the Gaussian model, Gaussian distribution for the cluster. So it works very well, even though we have the missing data. like the other the data mining algorithm, it works very well. However, just like the k-means algorithm, sometimes it can convert it to the local maximum. Okay, so which means it is not actually cluster. It's you know what is the local the optimal. Local optimal is the if we have the one-dimensional value like this one, so we have two clusters. This is our goal. But however, if we have such a small curve, but we can ignore such a thing. However, unfortunately, if we decide the first time this is a centroid, try to form one cluster. Okay, so if you have the initially two cluster in your EM clustering algorithm model 2 model, so you cannot get out from such a local optimal. So you should be careful. That causes the same problem as the what? Number of cluster. Okay, number of the model. Number of how many Gaussian model in this data set. In this that is the general problem in such a cluster. Okay, and relatively, so we need a large data set, and also it takes a little bit of time.
Professor?
Yes.
Could this happen even if we smooth the data in the
Yeah, that's
data
one of the
clean?
solution. Okay, to address the problem of the local the optimal, so you can smooth like this. Okay, that is one of the what we can apply the regression model to from the statistics. Okay, that's one of the solution. Okay, but still, the EM clustering algorithm provides a reasonable result. So in the clustering, the data mining algorithm. But nowadays, the research article or technical paper, research paper, they try to use the classification algorithm nowadays. Not many the clustering because it's hard to apply in real problem, real application. It takes a time. In terms of accuracy, it's not better than the classification. So in the real product, real application, the classification is used a lot nowadays. That is true. But I like that the clustering algorithm. So I'm going to skip the clustering high dimensional data, so you can start by yourself. Then jump to the graph. Okay, clustering graph and network. This is the very important task nowadays because of the popularity of social media network. So as you have heard the last time, even half of the idea, half of students select the social media data for the term project. So we will see such a clustering the graph and network data. Okay. So first, the application, definitely social media data, the social network. So for example, the Facebook, we can represent the Facebook the data with the graph. So those who already took the NoSQL database, one of the example of the NoSQL database is a graph-based database because of the popularity of the social media network. So social media, as the name implies, social media data, social media network is based on the network. Okay, social network, as the name implies, social network between whether we have the relationship like the friend or the follower or the followee, so that the relationship can be represented by the graph. Also, the graph can be used to track the behavior in online, like the user click the page, HTML page, then it has a lot of the hyperlink. But those who select this one and this one will select the this is the car. This is the what is that? for example, car and cell phone, we select the iWatch. Okay, like that. So how can we represent such a user behavior? As you can see, we can use the graph. Like this one is the node, and the relationship can be represented by the edges. So we can use such a graph data structure to represent the social network. Also, bipartite graph used a lot. Anyone who heard about the bipartite graph? Bi means two. We have the two set of the graph. So bipartite graph is the new. It's not the new one. It's the based on the set. For example, we have the customer data set. We have the item data set. So we have customer 1, customer 2, customer 3, customer 4, and item 1, item 2, item 2, 3, 4, 5. So customer 1 purchased the item 1, item 2. Customer 1 purchased this one, this one, this one, this one, this one. So if we can find, so in bipartite graph, we have the two set of the nodes. So in general, graph can be defined as vertex and edges, right? Set of nodes, set of edges. But in bipartite graph, we have two, V1 and V2, and edges between V1 and V2. Our goal is to find such a edges between two set of the nodes. So if we can find something pattern, for example, those who like the C1 and the item 1 and item 2, mostly they'll purchase the item 3. We try to find a similar pattern or something like that. Also, the bipartite graph can be used for to measure similarity. So one of the example of the using bipartite graph in the data mining is the, do you know the DBLP? DBLP is a database for bibliography. Okay, bibliography is the references, the paper author name and the paper name and the publisher and something like that. Sometimes my name. Google try to find if you for example this one, so Google find bunch of paper which are not related to me. But how do they find whether you can see J.Y. Lee considered as my name, because sometimes my name is represented by the J. Lee or J.K. Lee or J.U.N.G. Lee and J.U.N.G.K.Y.U. Lee, or sometimes J-U-N-G space K-Y-U Lee, different way, but all of these are my name. So they match not only the name, okay, so this is author information, this is a paper information. So I know it's a paper and paper 2. So paper 1 has the author name and some affiliation, the University of Bridgeport, something like that, and some topic. Then try to how many of them are matching using bipartite graph. Okay. Then we can measure the similarity between them using this bipartite graph. But many of them are false narratives. I don't know why so many. Of the last name. Okay, so that is the graph. In the graph, the processing, we need such a similarity measure to compare the subgraph. We can compare the entire graph, or we can compare the subgraph. It's a part of the graph. Sometimes we can compare node by node or edge by edge. So we are going to take a look at the two similarity measure. One is the geodesic, the distance. Another one is the distance based on random walk, which is called the sim rank. Okay. So there are many the graph clustering method. So try to, for example, from the Facebook. So whether Facebook graph for my friend, whether we can make the cluster by similarity, like the friend group, like the family group, or the college friend group, or the high school friend group, something like that. So we will see. We are going to see the geodesic, the distance first. So there are different definition in the geodesic similarity measure. So for example, the eccentricity is the, for example, eccentricity of the node. Okay, the largest geodesic distance between V and any other vertex. So for example, the A is the largest distance is 1, 2, the degree, number of degree. And from D, the largest distance is 1, 2, 3. So D is 3. From E, 1, 2, 3. That is the eccentricity of the node. And radius is the mean value. Okay, mean value of the eccentricity. For example, from in this graph, the A is the minimum because it's 1, 1, 1, 2. So it's a 2. 2 is the minimum, the eccentricity in this graph. So it's called radius, and diameter is the largest one, the maximum. For example, from D or from C, from E is the distance is 1, 2, 3, 1, 2, 3. So 3 is called the diameter. Then if the set of node belongs to such a diameter, that is called the perpendicular vertex, is kind of the boundary. Okay. So using such a thing, so we can define the similarity sim rank. Okay. So it's similarity based on the random walk on the structured context. So it is based on the structural context. So we are going to use the graph structure as I did. We are not going to consider any attribute itself. For example, if we had this is the node, the lead. Okay, I have the friend. The three friends, we never, after make the friend, we never exchange any message or any like or any favorite, no, just the three. So there's another, the student or the Facebook user who has the three friends. They send a message every day, every time, and they whenever they post a message, it's the likes every time. So can we say that this is the same as this one? That this node, the lead and the user A is the same. So if we consider such a structure of the graph, structural context, it's the same. Okay. Otherwise, if we consider such a strength between the node, okay, how much strength, kind of attribute. So that is the difference. Okay, that is the characteristic of the structural context. The sim rank is based on such a structure only. However, you may fear. So which one is better? We cannot say. For example, if we need to consider such a context of the node or the feature base, so sometimes it's very hard. How can we define such a strength of the relationship? It's a number of comments or a number of likes, or sometimes what if they are fighting each other? Okay, so sometimes we can just consider such a context that makes sense. Or sometimes depending on the problem, you need to consider such a the feature. You need to characterize the node and edges. So this is based on the such a structure of the graph. It's sometimes called the structural contextual similarity measure. Okay, how can we do that? So mostly whenever you are using or whenever you read a paper or the approach that are based on the graph, they define the graph G is the graph set of is a graph. This has the set of V. V is the node and set of edges. The edge is the relationship between two nodes. Okay, so G is the V and E. Then at that time we can define that in neighborhood means in neighbor. So from this one. So in neighborhood of this one is this one and this one and this one. Okay, from here to here. And if we vice versa, that is the out neighbor. Our neighbor is the V is from for this. So and for this, what is the V? What is the W? So that's the. But mostly we are using the in neighbor. Okay, for the measurement. And when we compare U and V is the node. Similarity of the two nodes. How can we compare? This is a good example. So if we have the same structure, it will be the same. Otherwise, different. So this is. Can you understand what that means?
Which one?
So this one. Similarity of the two nodes. S is first we are going to take a look at what is the S. S is U and V are the same is 1, otherwise 0. So for example, this node and this node is the same node. Okay, share the same node is considered as the 1, otherwise it's 0. In other words, how many common nodes from neighborhood of the U, neighborhood of the V. Okay. How many common the neighborhood? Okay, I have a friend. He has a friend. How many common? Okay, all of them are he. We have the 3 friends. So they are my friend also. They are his friend. So he and me will be considered as the exactly same. Okay, that is the normalized. There are 2 students who are sharing the same friend. So 100 friends are the same. Okay. That is maybe different, the quality, right? So we have only 3 friends, but they are sharing 100 friends. So it's much the strong. It's stronger than our relationship, right? So it's a normalized. Normalize the common, the neighborhood node. But it can be represented as such a equation, mathematics. You will see a lot of such how to represent the common, okay? And how to normalize. It's a divide by the number of the in neighborhood. So how many neighborhood nodes? Okay. Then it will start from the 0 initialization. Then keep the increasing. Because it will be start from 1 degree, 2nd degree, and 2nd degree friend of friend of friend. Okay. Something like that until it is not changed. Then this is considered the sim rank. Similarity rank. Okay? Similarity based on random walk. At that time, this one is considered as the expected. It's a probable here. If we have the 2, for example, this one. So if we can find such a node to travel, that is this one from U to V. So U to the V. It's a travel. So one node and another node for each. What is the probability of to select among these? What is the probability of this one to select this? And we have this. And what is the probability? And so on. Then we can the sum of such a probability. Okay. Then we would have the some that is called the expected meeting probability from U and V. However, somebody, so this one looks like a very complicated. Somebody prove this one actually is the same as this. So we don't have to compute it this way. We can just use such a sim rank to compute the similarity based on the context structure. That is your third homework. Okay, it is I think the exercise 11.5. The sim rank is the similarity measure for clustering graph and the network. Proof. So we can limit this step from 0 initialization and to the end we can limit. That is the sim rank and UV is a converge. Okay, it has a limitation. Also that the sim rank is the same as the expected meeting probability. The reason I assigned this one for you is sometimes I can feel that many of the researchers ignore the importance of the formal way of proving. Okay, so you can find the solution actually from not the internet. So it's a reference. So this book has the huge amount of, this is one of the benefit of using this textbook. It has a huge amount of the reference. One of the reference has the solution of the proof, 11.5, okay? And why don't you try to understand? Just you don't have to prove by yourself. Even I cannot do that. But try to understand how they prove such a, it looks like that obvious sometimes, okay? But by proving your idea mathematically, you don't have to actually the experiment, you don't have to do that because you prove using the mathematics, your idea. So 11.5 is your homework, master homework. Actually, the homework is to find the solution from the reference. You don't have to try to prove by yourself. Okay? Instead, why don't you find the reference paper, okay, that proves, then try to understand. Okay. Then, after we define such a similarity measure, say 11.5 exercise. Do not try to solve the problem by yourself. Okay? So it's you need to find the reference paper that prove that answer to this question. Okay, then
Does the second edition also have the same problem?
I don't think so. I don't think so. Second edition does not have that question. The third edition only. When I check the second edition, it doesn't have that question. But it's just a 3 or 4 length. So you can ask, if you do not have the textbook, you can ask the other student. So graph clustering we can define. So why don't it's here. So how many groups can you find here? 1, 2, right? How can you make a group from the graph? You need to cut this way, right? You need to cut the edges. So that is the reason the graph clustering means graph cutting. How to cut? How to cut the graph to get the group of the data. If you cut this way, can we say this is one group? It's hard to say, but it depends on. But it's hard to say. So we are going to find. So what about this way? If we cut this way, it's too expensive. It's too dense. So our goal is to cut the edge which are sparse. So that is the reason it's called in general the graph clustering. The problem of the graph clustering means finding the sparse edge, then cut them. Okay, that is the graph clustering algorithm. So minimum cut does not provide always the good partition. Okay, so even though this is one edge, that doesn't mean it's a good clustering, good cut. Good cut means overall it's a sparse. We try to find such a sparse set. Okay, so our goal is to find the in the graph clustering. So our goal is to optimize such a modularity. Modularity means it's the one module which is connected very strong. That is called the modularity. How can we measure the quality of such a modularity? This is the measurement, quality measurement. How can we understand that? First, the L means edges between vertex in ice cluster. In the cluster, edges. Okay. Then D is the sum of the degree of the vertex in the ice cluster. Degree means in this cluster, 1, 2, 3. What is a 1? So 1, 2, 1, such a degree. The higher degree, the better. No, higher degree means it's 2. The maybe sparse, right? So it's a penalty. So that is the reason it's a minus. Okay? So sometimes you need to make such a equation or your destination function. How can you find? So if you want to normalize, it's a denominator. Or if you want to penalize, you need to minus. And at that time, sometimes it's the square. Okay? Sometimes power of 3, power of 4. You need to determine such a degree. Okay? So if you give the same weight as the edges and vertex, the edges and degree, you lose a lot. It's too high. So you need to, sometimes empirically, you need to find the optimal such a function. So I think, and then for each cluster, this is our quality cluster. We try to maximize this modularity when we cut. So once we decide such a quality measure, so we can decide whether after we cut this one, whether the Q value is decreased or increased. Decrease means which is not good. Increase means it's better. Okay, so that is the graph cutting. Okay. Problem, just like the other graph theory, many of them are NP hard problem, which means it's a brute force way, no optimization. Okay. However, nowadays, by considering there's some constraint, you can make the optimal solution of the graph. There are many variants of such a graph cutting, graph similarity algorithm. One of my he was not my committee member, but I took his the machine learning class when I was a student. He actually did the purpose in his dissertation for the PhD. He proposed the subgraph matching algorithm one. Then he has been used almost 30 years for the same equation. Sometimes he applied that graph coding for the database search. So he proposed the graph database, and based on his graph searching, subgraph matching, actually subgraph matching algorithm for graph database. Sometimes apply image processing. Sometimes apply the DNA sequence. Sometimes apply. So he has been used only one application entire his life. Then he was very, very successful. Right now, he is the dean of the University of Washington. I forgot the name of the campus, but he is in University of Washington. And he got a lot of grants from NSF, DARPA. They're using only one, the graph matching, subgraph matching algorithm. Okay. And nowadays the graph is not that simple. It's getting complicated. Like we need to consider weight and something cycle, especially the weighted graph or direction. Also, we need to consider the direction. So for example, the tweet data, Twitter data information are those directed, right? From the follow it and follow. It's like that. And mostly the graph thing is a high dimensionality. Why is a high dimensionality? Suppose that we have the millions of the graph. So we can represent the edges and graph using matrix. 1 million by 1 million. It's a huge the matrix. So it's called, it can be considered a high dimensionality data. How can we address that problem? We can apply dimensionality reduction. So algorithm such as a PCA or the covariance method. Okay. And also, large graph is open sparse, which means it's too big. So it's very hard to find the characteristic. There are a lot of noise data. So if we, I think the one of the Abdullah shows the one graph, example of the graph when in the page 2. So it's just one the volume. We cannot see the details of the graph structure, the characteristic. It's a sparse. So we need to address such a problem when we process the graph. Okay. So we already seen the such a approach in the before. That is a scan, DB scan and scan. It's a density based. Okay, approach. We will take a look at that example. So, for example, from here, whether this is the such a related one, yes or not. So we need to check. So otherwise, we are not going to consider this is a part of the disk. Then start whether connected. So for example, at that time we can consider the structural similarity. This is nothing but normalize the common the neighbor. Okay, so B neighbor of the B and neighbor of the W and their common and the number of their common. Okay, and normalize by their the number of edges, the neighborhood. Then this is the similarity. So, for example, this is the same as the DB scan that we have seen before. Density-based cross-running algorithm. So we can start from here. So, for example, this is less than the epsilon. Epsilon is the relationship. It's a given data. So we have the how many? 13 node. This number. The 14 node from 0 to 13, and we'd like to start from one of the node and check what is the closeness. So it can be the attribute value or the feature vector, or the, for example, in case of the Twitter, then how much two users, tweet users are similar or share, something like that. It's less than the threshold value, so we will consider this is the outlier. Then from the 8 we move to the 8, then it has the 0.8, 0.7, which is bigger than the threshold value. Then we will consider these three are connected. Then we can say if the 12 and the 9th are the bigger than the threshold value, it can be considered as the click, the smallest module. Then keep checking. Here from 12 to here is not, but because of 8 and 9 is connected, and check this. Okay. Then 6 is the between two groups, so we can say this is a hub. So we can actually use this one to cut, to separate the group, and something like that. So this is the same approach as the DB scan that we have seen in the density-based cluster. So, what is the complexity in terms of big O notation? It's n, right? You visit 1, 2, 3, 4, 5, 6, n. Somebody may be curious. For each node, you need to check what is the less than n. Okay? So we don't have to worry about that. But in the big O notation, it's just n, which is much smaller than n squared. Okay, so that is the benefit of using such a scan. Okay, I'm going to start the clustering algorithm here. So one more thing that I'm not going to cover in this class, but we can actually give you. This is a summary of the advanced clustering algorithm. We have seen the fuzzy probability relative the model base and the EM algorithm. But in broad view, all of them are the same approach. Okay, and we have seen the graph and network data. There are many variants of the graph clustering and the graph matching and graph similarity algorithm. So if you are doing the research on the social media data, why don't you think about the graph-based approach also? Okay, that will be helpful. Conceptual clustering. So I had a lot of interest to use the conceptual cluster because I have used for the data set, I have used the video data set.